So this talk is about how to get safer C++, and I'm reporting from my experiences on participating in the MISRA-C++ guideline stuff and the AutoStar C++ guidelines, and also some the general C++ programming language vulnerability guidelines that I'm working on. For those who haven't seen me before anywhere, you see my coordinates there, and I'm available for consulting, training, and coaching and reviews, everything about C++ and Agile. Now, if you look at safety guidelines, what does that mean, safety guidelines? You might all have heard about the C++ core guidelines and have maybe follow those guidelines in your C++ code. And what's come with those guidelines is they try to limit the use of your language. One big problem with safety guidelines is that usually most of the safety guidelines, regardless of the domain of programming or other things like aviation or automobiles, they usually stem from incidents that have happened, hurt people or even killed people, and then analyzing the root cause and trying to get a guideline to prevent the root cause in the future. For example, if you've flown any jet airliner, maybe not last year, but in the years before, you might have recognized that all the passenger windows are actually rounded, so oval, in an oval shape. And that stems from a time when the actual first airliner with the pressure cabin was constructed and flown. It was quite successful until they had crashes, and then the analysis of there was not just only one crash, but I think several. The analysis of the fuselage pointed out that the actual crash was caused by weakening of the fuselage from the corners of the then cornered windows, because the planes without the pressure cabin did have rectangular windows, because that is a typical window shape we are used to, and they caused stress from the corners of the windows. And that was something figured out after the fact. Again, also with software, we might figure out after the fact what went wrong with code that we actually write. And safety guidelines try to prevent problems in the future, and that is why we have them. So where is safe C++ applied? C++ as a systems programming language happen to be used in many kind of systems where actual technical facilities that might harm people occur, be it factory automation, automobiles, trains, aviation, and whatever, traffic control systems, and that's where all kind of safety critical system software is created. And the guidelines for C++ are a tiny part of the how to get those systems operate in a safe mode, and the risk of harming people is reduced. So what is safe C++? It's what I consider today, we strive for having a good C++ plus more, where actually that more means less. The safety guidelines try to limit the use of the language to actually make it less risky. And risky, what can be risky in C++? One major risky part is actually the situation that you might have undefined behavior, and undefined behavior leads to interesting program behavior, and interesting program behavior in a safety critical system might mean people get hurt. So where is it come from in the software domain and in general? Usually the domains where it's safety critical because of past experience are highly regulated, and the typical regulation process and standards, they prioritize process and documentation. And one reason for that is to be able to figure out if something bad happened, to figure out the root cause, and maybe later on being able to better protect people by changing the guidelines and being able to actually analyze where the root cause was. If you have an arbitrary crash and only have the machine code of a system, it might be very hard to figure out the root cause. You might figure out the assembly instruction that caused the crash, but not actually how you got there. Maybe you can find the source code for it, but even the source code might have had a history on how it got there, and it actually was a process. One thing that we can see, even though the documentation process is highly regulated, the actual people might lack the technical expertise, or maybe the process might not lead to actual good software, or maybe even the guidelines themselves lead to software that has questionable quality. So you might actually follow the process, document everything, and still have crappy software, which is something that got me into actual getting into the standardization of MISRA-C++ and the AutoSAR C++ guidelines, because there have been incidents of software maybe written in C that actually was following guidelines and still was not well enough. You could say they didn't follow the guidelines by heart, only by letter, but nevertheless, good guidelines and good code go hand in hand. So the thing is, if you follow the guidelines and you can prove that you followed the guidelines, your insurance has to pay, and sometimes management is just looking for that. And we've seen where that leads to, like what happened with the, for example, in aviation with the Boeing 737 MAX. If you look at, so people actually care about safety. There are big safety guidelines, like the European norm 61508, which is all about, that is electronic and software control. There are other norms, especially ISO 26262, which is has to be used in automotive sector, and other guidelines for the general overall development of safety critical systems that happens. One thing that came out of the safety guidelines is the so-called V model that some of you might have seen already in the software development process, where you have the on the left-hand side of the V, the stages or the phases that might lead to a good implementation. On the right-hand side of the V, you will see the actual how to verify the things, and usually today we would have unit tests, integration tests, and system tests, and corresponding feedback loops that go across the V and around the V, and have an iterative implementation. For since you cannot develop all the software to the highest level of safety integrity, most of these guidelines define the concept of the safety integrity level, which means, okay, the higher the risk and the higher the chance of hurting people, the higher the software integrity or the integrity of the general system should be. And if you, let's say in a car, if you have the entertainment system, that usually is less safety relevant unless it's interconnected, but the anti-lock brake system, that is highly safety related, so that shouldn't either break unintendedly or break too much. That's all kind of where the higher level safety integrity level is important. So for example, usually we have 4 to 5 levels, where the lowest level usually means, okay, it's not very critical, and the highest level means, okay, it's highly safety critical. So anti-lock braking system software would be would need a high safety integrity level, and maybe the passenger seat control to change to actually change your seat position might be a lower safety integrity level. But I'm speculating here only. I'm not a car software expert. To achieve safety, especially in software, what you have to rely on is actually fault tolerance, because it's not only software that fails, but also parts of the overall system that fails, and your software must deal with such failures. So there's a nice book I want to give you a reference to. It's called Patterns for Fault-Tolerant Software Systems by Bob Hangner, and it's quite old, but as a patterns book, it has timeless knowledge in it, and it gives a lot of terminology and also concepts on how to create fault-tolerant software. So if you have software that operates 24/7 on a server side, even if it's not safety critical, but critical infrastructure, you better be aware of the concepts presented in that book. So fault tolerance is not only a problem with safety critical, but also with systems that rely on highly operation, but especially critical for a safety critical system. So what you can learn is that safety is like security, a multi-leveled approach. You have multiple levels of, if some subsystem fails, you better have another system taking over and having a safer mode to go onto. For example, for a car, if your engine control is getting in a failure mode, that happened to my car sometimes, and then you are only allowed to drive slower and the engine wouldn't rev up as it would normally be and have reduced power, for example. And again, if you consider aviation, most of the time a jetliner will fly on autopilot and the pilots are actually only there to control that the system flies well enough. And if there's a failure mode, then the system will get the pilot the chance to take over, or will even ask the pilot to take over to fly manually when that's possible. In the fault-tolerant system book, there's so-called units of mitigation, where you actually not only have the layered system approach, but also compartmentalized system approach. When one subsystem fails, let's say in an order system by Amazon, if the bill generation fails, you still might want to have the ability to send out shipments and then send the bill later afterwards via email, for example. So these units of mitigation is about, okay, if some subsystem fails, the rest of the system should degrade gracefully and not just crash or not be available. One of the concepts of fault tolerance is having redundancy. So you have extra parts. In engineering, you have, let's say, redundant parts that are either take over as a replacement, or they take, or where you have more than needed parts. For example, a jetliner with 2 engines, one engine might actually fail and it still is able to land safely. That is a typical redundancy. You wouldn't find you would find not many commercial airplanes that only have a single engine. If those, then they still have the possibility to try to land safely as a glider. So in software, redundancy is kind of a tricky part, because you also don't want to have needless code. That means the code size gets bigger, and the bigger the code size, the higher the probability of errors or bugs in the code that falls in the code that might lead to later failures. One word of caution: if you write fault-tolerant software system in C++ or even C, the standards and the compilers expect a perfectly working abstract machine. If your code has undefined behavior, or let's say exceeds the limits of what the concrete implementation of the abstract machine is able to handle, then you are outside of what the language itself can handle. And if you try to mitigate that from within the language, you will fail. I have seen code, and there have been some prominent things where code tries to prevent undefined behavior with extra checks and if statements, where unknowingly those if statements and extra checks actually incorporate undefined behavior themselves, and thus all the code that did the checking and the other was actually removed by the compiler during optimization, or didn't work because of that undefined behavior, and the actual checks and balances didn't work. So, for example, you cannot detect that the hardware is that your hardware memory is failing from within C++ itself, because the abstract machine will assume that the hardware is perfect. You need error checking memory, for example, to be able to detect those bit failures, for example, in hardware. You cannot write C++ code to detect bit failures in the abstract machine, because the abstract machine is presumed to behave perfectly. If you look at coding standards and their history for C++, there have been a cross-influence and kind of a feedback loop on things. We have general guidelines for C++, like the C++ guidelines by Herb Sutter and Andrea Alexandrescu. We have the Scott Myers books, the old ones and the newer ones. And we have now the C++ core guidelines. And those kind of guidelines and even C programming guidelines influence what's currently known as guidelines for safety critical code. I have a slide on the history of MISRA-C that influenced the Joint Strike Fighter C++ guidelines and the more modern high integrity guidelines by Perforce, and we have the older, still current MISRA-C++ guidelines from 2008. And since those guidelines were based on C++ 03 and older code, the AUTOSAR consortium with it, which is a consortium of automobile manufacturers that try to have a common platform for their software systems within the car, they judged it's time to have a new C++ guidelines, and they started out to do it for C++ 14 by inheriting a lot of guidelines from MISRA-C++ and modernized those that they thought were reasonable to modernize, and added some new for the more modern features of C++ influenced by the core guidelines. We hope to have MISRA-C++ guidelines ready in 2021, but I'm not sure it will happen, because most of the work done on the guidelines is by volunteers, not being paid for that, even though some have a role in the tool vendors or the automotive industry that participate. It's kind of an extra job and not something where you would start out and like a book project where you start out and from start to finish and then have a review and you're done. So it's still a lot of work to do, and some of the guidelines I will present today are more like, okay, these are drafts and we will change them later. I would like to notify you of another ISO working group. It's not WG21 for C++ standardization, but actually the C++, the programming language vulnerabilities working group that have a guideline on general, let's say, programming causes for programmer bugs, like index out of range, for example. And there's the -10 sub-project document that will collect and specify how these general problems occur in C++ or don't occur in C++, and how to mitigate the situation in C++ in general. It's not directly related to safety only, it's just directed to, let's say, well-performing code, and that's most important in security and safety critical systems. So what are the guidelines actually addressing? When I looked first at MISRA-C++ 2008, I had the impression, okay, it's about how to write non-breaking C++ for programmers who know C and only a little bit of C++. And okay, if you look at real-world industry code, maybe not by people attending ACCU, but those who are not aware that they can improve their understanding of programming and C++, they might have misunderstandings on how the language or the compiler actually work. And There have been misunderstandings that have been observed by incidents, as we have I've told you before. Bad things happen, and then okay, you analyze, and those bad things that happen, so misunderstandings that happened, are tried to address by such guidelines. The other big thing in C++, we have the concept of undefined behavior, which is a great thing and occurs itself. So those are the things to prevent getting into the situation of undefined behavior. And MISRA-C++ is also addressing stuff that relate to implementation-defined behavior. But as we all know, we cannot program in C++ without relying on implementation-defined behavior. Like whenever you use int, it's actually available values, and behavior depends on the implementation. If you're on 16-bit, 32-bit, or a 64-bit machine, and even what compiler settings you are, you might have different bit widths of int. And the guidelines there are either preventing implementation-defined behavior or actually force you to document when you rely on implementation-defined behavior, so that it's clear what that a reviewer can actually check the intent of the code against what's available on the target system. Sometimes one can argue, okay, the safety guidelines try to address checkable rules. It's much easier to have a static analysis tool that mentions to you, oh, here you have a problem, than something that only a human reviewer can actually check and maybe document, okay, I believe that this rule is fulfilled, but there's no means to actually prove that. If you're into, let's say, computer science theory, you know that there are questions that cannot be answered by a machine, cannot be actually proven. So the only thing that you might end up is having a best guess that something is true, or that the risk of it not being true is so low that you can live with that, because there's no risk-free life at all. So a lot of rules are telling you what not to do, and they are not as constructive in telling you what actually you can do. That is because the guidelines, especially the MISRA guidelines, don't want to limit your design space too much. They only limit how much you use the language. In my personal opinion, more guidance can be helpful, but that is not the role of the actual MISRA guidelines. For that, you have to hire the corresponding consultants, or maybe get the additional knowledge on a more constructive way on designing the system to be safer. I try to sneak in sometimes some of the more guideline-ish rules into the MISRA guidelines, but I'm not always successful. If we look at what do guidelines check for, if you look at the whole system, what you can actually express in C++, you see that we have the C++ grammar, and that is much broader than what is accepted by the compiler. And for those of you who might have seen the C++ standard and look at the grammar rules, if you just implement the grammar rules, you will accept programs that won't compile. So actually the C++ standard had a lot of text and explaining which subset of the applicable grammar rules is actually acceptable programs. There come things in like the type system that checks for validity of expressions so that types are okay. There are semantic rules and other, let's say, slightly semantic syntactic rules where things are forbidden to be used, even though the actual underlying language grammar would allow them. We have then a subset of that compilable C++ programs that are actually valid C++ programs without undefined behavior. The compiler is not obliged to actually detect undefined behavior. That's why it's undefined. If it would be easy to detect, it would be saying the compiler would be able to just say, no, this is invalid. There are other things where compilers provide you with warnings, which are kind of guidelines. Typically, warnings stem from the experience of programmers did bad things, and it's not probable that any code that contains this bad thing is meant to be like that. Like having assignment statements in an if condition can be something that was accidentally used. You would use an equality comparison instead, and that is where compilers will actually warn you about that, even though it's perfectly valid and C++ without actually being an invalid program. But it might not meet programmer's intent. And guessing programmer's intent is something sometimes what the guideline rules do as well. And they also strive, and there are other guidelines like the core guidelines that limit you even more by saying, okay, these are practices that you don't want to do because it makes your code no longer understandable or not easy to understand, and others working with your code or even yourself might no longer understand. Like saying, okay, I write a function that is 100 lines long with a deeply nested if conditional statements. That is something that might be perfectly valid and perfectly correct C++ code, but it might no longer be understandable under maintenance or even by a reviewer who does a code review to check if it's actually doing what it's pretends to be doing. Also, such long functions would make it very hard to test exhaustively and guarantee that they're not doing the wrong thing. Then the concrete safety guidelines as enforced by a static analysis tool might even provide a more subset to what is understandable and safe. That means you might actually want to write code that is understandable and safe and violates one of the guidelines. So all of these guidelines have a kind of a deviation process, even in the safety environment. So you can violate a guideline if you have a good reason for that, and that reason must be documented. And that is a good thing to do. So don't, and sometimes even guidelines seem to disagree because you might violate one guideline and then another guy, or you might actually have a guideline that cannot be violated because there's another guideline that covers it already, but that other guideline might need to be intentionally violated, and then the second one actually kicks in as a fallback to make sure you don't land somewhere where you have undefined behavior. All of the checks that you might get from a compiler or a static analysis tool might incur false positives. And those are ones where you have to deviate because you might want to have your code written like that. So be aware there might be checks that you think, oh no, that's ridiculous, that this is a warning or this is a guideline violation. But you should think twice before just disabling the check and figure out if there's actually a reason that your code might be violating the guideline. So that is kind of the hierarchy of possible things that might happen and what guidelines actually address. Now let's look at the more what's entry there. If you look at some of the guidelines history, especially the overarching, let's say, software stuff that stems from very early ages of software being used for safety-critical system, there have been some recommendations that come from an obsolete time when, let's say, structured programming was not yet standard practice. I think people doing software today have a hard time remembering that, but maybe those who are my age and grew up with programming in BASIC, that was quite easy to write a not well-structured program in the 80s on your home computer. And from that time, when there wasn't structured programming yet a thing, there came the concept of the single entry and single exit principle, which means you have a block of code and you always start from its beginning, and there's only a single point where you leave that sub-program. In assembly language, that would mean you jump somewhere and then you jump from that piece of code somewhere else. And you always have a single point where you jump to on a given block of code and a single point from where you jump out of that single point of code. That is what the single entry, single exit problem originally stems from. That in the age when structured programming, nobody would even think about doing no unstructured programming, that was translated to okay, a function should have a single point of entry and which is a given because you call it and that starts the function, and a single point of exit, which is return. And that transforms to, there must be a single return from a function. In general, that leads sometimes to very crazy control structures and even the use of Go to make sure that you have the single return statement. But that's a wrong translation of the original principle, because a function is a structured programming construct. You always call the function, it starts from the top, and return from the function exactly to the call side. So you always return from a function exactly to the call side. Even in C++, when you throw an exception, it will take you to the call side and then unwind the stack until it finds the corresponding handler. So there's always a structured way of how the control flow works. And so the single entry, single exit principle is always adhered to by a structured programming language. MISRA-C++ 2008 was written by a group of experts, and some of them C++ expert, but not all of them. And because it assumes, okay, the industry practice are now, not all industry software developers that work in safety critical systems are actually C++ experts. So if you look at today's view from C++ 20 or 17 or even 11 on the MISRA 2008 rules, a lot of things there that are explicitly addressed shouldn't occur at all in modern C++ code, like the use of new and delete, or even the use of free and malloc, which is explicitly verboten there. And I talked about the conflicting rules because of the multi-level safety, where you deliberately suspend the checking of one rule and have another one that kicks in as a safety net. And again, remember, you cannot check for hardware errors because of the abstract machine is assumed to be perfect. I explained most of what is on this full side about the single entry and single exit principle already in words. Sorry for that, I forgot to flip over. And this is a table to show you a little bit, okay, there are these different levels of safety and different means of getting a safer code. And if you look at the right-hand side, almost all things are obligatory, meaning maybe these two pluses. I'm not sure if you can see that. And if you have a less critical part, only some of the stuff is obligatory and just recommended. And this is another table that is more readable. They say, okay, limit this module size, that, okay, a 100-line function might be a little bit too big, and that's highly recommended regardless of the integrity level. And encapsulation, information hiding is highly recommended and only recommended for a low integrity level. So the single return statement in a function is cow-manure, because you no longer program in a way where you have steps like assembly statements and arbitrary jumps somewhere else, even jumps in the middle of a function. Again, I know that C++ coroutines will change that leaving and returning, let's say, invisibly, but that's a different story to be tackled later on when the safety guidelines actually, when we got enough experience with the usage of C++ coroutines, and the safety guidelines have to address the misuse of coroutines. So today we have functions, and there's by definition a single entry, the function call, and a single exit, and we can replace a function with something else, and it still behaves nicely. An example where the perfect abstract machine is actually making your code being optimized the way that is put in as a safety guideline. If you have plain old C-style enumerations, which are actually forbidden by MISRA-C++, or will be forbidden by the new MISRA-C++ guidelines, then the compiler is allowed to assume that any variable of that enumeration type will only have the values either of S0 and S1. And that your program, because you're a perfect programmer, that's the underlying assumption of C and also of C++, doesn't make a mistake. The compiler can assume that a variable will never actually reach a value that is not one of these enumeration values. So when you write a switch statement based on that variable, and have a default case to say, okay, if something bad happens, either a bit flip or something interesting, a memory override by undefined behavior, then I detect that with the default statement and exit my program. And in that function, you just flip from one state to the other, like a flip-flop. And if you look at the generated assembly code, there's no call to exit here because the compiler assumes, okay, this is an unscoped enumeration without an underlying type, so an old C-style enum. It can only have S1 and S0 as a state, so that default state is dead code. It can never appear, so I don't have to generate code about that default state. And that is where actually the perfect absolute machine kicks in, and the compiler tells you, oh no, you cannot have that. So one means is to make this an unscoped enum with an underlying type, specifying colon int, for example, or making it an enum class type where all the values of the underlying type that is perfectly defined will actually be allowed to in a variable, and then the default switch statement will actually cause the assembly code to actually contain the call. One myth about the MISRA guidelines is, oh, I have to perfect follow all the things that my static analysis tool is telling me to actually be sure that I'm MISRA compliant. That is not true. There's even a public document, so you don't have to pay for it, that explains to you the underlying process of deviation, where you can say, okay, this is a guideline that is too broad for my project, or maybe this guideline is outdated, it doesn't conform with our internal style guide, and we have good reasons to violate that, and you can document those reasons so you can deviate from a guideline, either in an individual case where you say, oh, for example, I have to use an old style enumeration type because this header where it's defined is also used in C that doesn't have the enum class types or specify the underlying type. So this is something where you can document the deviation, and then you have to ensure that it doesn't cause any subsequent problems in your code base. There was an idea to standardize a MISRA attribute that would actually allow us to specify deviations in the program code, but that is, I think, is not happening for the next MISRA release because the existing tools have other means to suppress guidelines individually, usually with special comments, and that might not happen there. Maybe the vendors get together and define such a common but it will not be defined by the MISRA guidelines. The big thing in safety critical system is that any deviation or the justification must be reviewed. And as we have seen with the aviation industry, the reviewer should be an independent person, not just the one that actually made the deviation. Some on slides that I borrowed from David Ward on the underlying mission. So it's the original MISRA is more than 25 years now, and it's for providing guidance to actually write safe code in safety control systems, especially in embedded systems. And most of the time that's standalone code, so that requires on compilers and so-called freestanding implementations, but we also see today that, for example, in the AUTOSAR C++ underlying system, the AUTOSAR adaptive standard requires an embedded Linux system. So we have a full operating system. Other safety critical code would use VxWorks or QNX, to name two of the vendors, or other real-time operating system, because usually if you have a control system, you want to know that you are able to turn off a problematic thing that might hurt people in a given amount of time, so the risk for hurting someone is reduced when the problem occurs. So what happened, because the automotive system industry is big and also was leading that effort, is that the actual MISRA guidelines for C and C++ were adopted across other industries as well. So you will find adherence to MISRA C++ guidelines beyond the automotive industry. You're not supposed to see that some of the major documents that you might actually already use or are interested in. This is the MISRA-C++ 2008 standard that's about to be obsoleted by the new one, where we work hard to finish it, but it's still a lot of work. That's a little bit of the history of the MISRA guidelines. You see MISRA-C is where the most active part happened, and AUTOSAR took over from MISRA-C++ 2008 and other guidelines that I showed you, and that fed into the MISRA-C++ 22X. And I doubt that the official release will be 21, but we will see. I hope it wouldn't be A like it happened with the C++ OX. Some older guidelines that might be no longer be exactly phrased like that. They might be superseded by some rules that are actually the same rule in new words, but sometimes it's superseded. For example, trigraphs shall not be used. Trigraphs have been removed from the C++ standards, so that rule might still remain because compilers might still support them, but actually, if you employ trigraphs, you're no longer adhering to the C++ standard. And one of the first rules of the MISRA guidelines is adhere to the C++ standard. And it even says the MISRA 22X rules address C++ 17, because that is where current experience comes from. We don't have a fully compliant C++ 21 compilers and languages in broad use, so there's not much experience yet in the additional vulnerabilities that might stem from C++ 2020. For example, I recently worked on the phrasing: if a function has internal linkage, then all redeclarations shall include the static storage class specifier. That's old terminology for okay, make a function that is not exported. And in C++ 20 with modules, you wouldn't say, okay, that's something that's not exported. In C++ 17, you would say, okay, instead of using static, we use an anonymous namespace to make to create a function without linkage. And that is a little bit how the actual phrasing is, to actually refrain from using static to specify functions, free functions with internal linkage. One thing that is used in old pre-C++ 11 software sometimes, and some compilers actually support its use, volatile, to communicate between threads or between signal handlers and the main program. That is something where bugs stem from, because you cannot use a volatile variable to actually communicate between threads. That is still undefined behavior until the variable is atomic. I just found an article on Twitter today where someone recommended to use just a static bool variable to communicate between threads, not even volatile, and definitely not atomic bool. And that is just such a cow manure that you wouldn't want to read on the internet. So don't follow those guidelines that tell you use volatile to communicate between threads. There are a few uses where volatile is still needed, but since they rely on stuff that's outside of the standard, if you have interrupt handlers or you have a memory mapped IO, or let's say you want to use volatile for memory mapped I/O registers, and since those rely on specific hardware that is underlying the system, you will have to document that you have to use that hardware. But in general, you shouldn't use volatile because programmers have used it to attempt to communicate between threads, and it's not working like that. It might just work on your compiler because your compiler knows about those undefined behavior and defines it in a way that works for you. If your compiler documents that and guarantees that behavior, you're free to deviate and document that you're using that specific compiler. But in general, volatile shall not be used. And one thing that's a general thing is don't write unreachable code. My personal preference, I showed that in my workshop yesterday a couple of times. It's something Kevin Henne introduced to me, and we both use that less code equals more software. In a safety critical system, code should be reviewed also by humans to make sure it doesn't do bad things. And that means you shouldn't write superfluous code that is unnecessary or even automatically provided by the compiler, and not rewrite the code that is actually created by the compiler. And in the official saying is, okay, a project shall not contain unreachable code, because that is something compilers can check, and it might actually be eliminated by the optimizers anyway if it can prove it's unreachable. But my guideline is don't write superfluous code, because the more code you write, the more is to review, and the harder is to make a very good review of it. It's very hard to review manually a 1,000-line or a 100-line function, or even a 20-line function. But a 3-line function you might actually be able to think through and guarantee, okay, it's doing what it's intended to be doing. AutoSAR itself contains rules which I appreciate. It says eastcons and ascons as possible. The ascons as possible situation is what we should strive for, because it's much easier to review code that is using cons and is actually doing good things. The eastcons part might be stylistic, but I still believe that it's a better way of reading declarations if they use eastcons. And if you really want to switch over between east and west, you can use cvelop. It has a refactoring that allows to refactor your code backwards and forwards between eastcons and westcons, and then you have to fight with your colleagues on who is actually doing all the reviews on the check-in diffs where you just flipped over the constants. Another thing what cvelop is providing you, I'm no longer proposing it. Let's say I'm still a fan of it, but I'm no longer can support it because I left the university last year, about a year ago. But it's still workable to add const qualification to your code, and there are corresponding rules in MISRA and AutoSAR, either for pointers in the old MISRA guidelines, but it will we will have inherit the rules that we that you should use const for your variables as much as possible. And that is something the MISRA-C++ guidelines will take over from the AutoSAR, and with the appropriate tooling, you will be able to actually automate the adding the const, or even have static analysis tools telling you immediately, oh, this could be const. And with cvelop, you can immediately fix it with a click. Now, some of the concrete examples, what we're working on. One explanation I have to give you, the guidelines come in different levels. There's mandatory rules like don't have undefined behavior. Some of these mandatory rules might be actually unprovable by a static analyzer. For example, there is no general proof that your code doesn't have undefined behavior, but it's still something you want to adhere to, and you cannot actually sidestep a mandatory rule. That is something you have to fulfill to be MISRA compliant. Most of the rules are actually required rules that can be deviated from, but they are a deviation should be done in individual situations, so for a concrete code situation, and it has to be documented and reviewed, both the documentation that it doesn't lie and that the code doesn't provide harmful stuff. In more general rules are advisory rules. They tend to be on the edge of design guideline. A project can select to completely adhere to an advisory rule, and many projects do so. Many of them can be checked, some of them cannot be checked. For example, an advisory rule might say, or a general guideline might say, okay, use good namings. That is something you cannot check. We are fighting to get rid of a naming rule in MISRA-C++ that tried to prevent using lowercase L's and O's, uppercase O's in identifier names because they can be mixed up. But with the introduction that we might get Unicode identifiers where we have homoglyphs, different letters that actually look the same depending on the font rendered, that is something it's very hard to check for validity, and also limits the design space of good names. And having numbered your identifiers by, let's say, having a very short prefix and then just numbering things. I've seen code bases like that. That is not, that is so obfuscated, which is something, it might adhere to such a specific naming rule, but it's not really a good name to be working from. Next level of rules are directives or documentation rules. We are yet undecided if the MISRA-C++ guidelines will use the term directive or documentation rule, where it says, okay, if your target system has specific features like implementation defined behavior or compilers that make volatiles thread safe, or because the hardware doesn't have multiple cores, so the memory is always consistent, the view of the memory, then you are obliged to document that, and it's something one cannot check with the static analysis tool. So an example of a mandatory rule, so the value of an object shall not be read before it has been set. That means that you don't read from an uninitialized variable. Some of the situations where that can happen are actually checkable, so a static analysis tool will warn you about that. But to make that, but in general, it's undecidable because checking the concrete control for that might happen requires solving the halting problem, and for those with a computer science background, you know it's impossible to solve that. So they are given concrete examples usually with these tools, and that's an example of a mandatory rule because reading from an uninitialized variable is undefined behavior. This is non-instructive. Another more instructive guideline, as the core guidelines might say, so always initialize a variable on declaration when you define it, and that can even be done for member variables today with the non-static NSTMI, non-static data member initializers. And so you can ensure that all variables are initialized. If you have that guideline in your project, you implicitly make sure that that is conformed to. Another rule we can talk about is, okay, controlling expressions shall not be invariant. That is also undecidable because the halting problem, and any if statement or loop statement where you have a condition, you shouldn't have something that's reading that always results in either true or false. But there are some statements that are exempt because if const expers will have to be compile time constant, so that by definition will always be true or false. And you might use code parts that are never used, like in code that is never actually used. And there are two exceptions that we see here. If you write in a control system, you usually have an endless loop that runs the actual control structure, and such an endless loop is typically formulated with the while true. And that is a loop where that is the core control loop, an endless loop, and that is never exited, and that's allowed. And there are some tricks with macros where you would have a do while with false. If you have never seen that, good for you. You're not using macros to generate code, but if you have such macros, they are allowed to violate that, because you actually never loop through the do while loop. Another guideline, internal linkage, that relates to what we had with the static before. Internal linkage should be specified appropriately, and it's on the level of advisory rule, because you might have a code base that is using static for functions throughout without using anonymous namespaces, and you might have good reasons to not change it, because adding the anonymous namespace is cluttering your code. That's why you can deviate from using anonymous namespace, but you could easily also refactor code, getting rid of the static specifying the linkage for functions, and use the anonymous namespace instead, which is this rule is actually guiding you to. And the problem is, why is static a problem? Why do we address that explicitly? Because it has so many different meanings. If you put static in front of a member function, it means it's a class member and not a function with the internal linkage. There are a set of rules on special member functions, and this is an innovation for the MISRA-C++ guidelines, because they didn't care that much. And it was the time when Scott Meyer's rule of three actually ruled. And today we have much more. We have more special member function, and thus much more variation that people might attempt to use well. And in my workshop yesterday, I showed what's the summary of this, that you actually have, the best thing is to actually use the rule of zero, to not have user declared stuff. And if you don't have to declare a destructor, and there are only 4 cases where you actually have to declare a destructor, then the rule of zero rules. Full stop. Just don't specify copy move operations and the destructor, and the compiler provided ones will be just right. There are a few cases where they aren't just right. One case, you have a base class of a polymorphic hierarchy with virtual member functions. There, if you put them on the heap, you have to have a virtual destructor, and for that, the virtual destructor shall be public and equals default. And the class must prevent copy or move operations. And there are 2 options to get there. And there are rules that specify how to prevent copy and move operations. One of my favorite, or one that I invented, is the rule of the mover. By deleting the move assignment operator, you will end up having your class to be non-copyable. For some cases, you might want to have when you have a mix-in base class that is intended to be mixed in but never actually deleted. There's still a fight on that, but there's an option to have a non-virtual protected destructor to make sure that there's no attempt to actually delete via the base class if it's used as a mixing class. There are other means, for example, unique pointer could actually check for the unique pointer derived to unique pointer base class conversion that the base class has a virtual destructor. Unfortunately, while that was in the original C++ OX specification of unique pointer that used the concepts of C++ OX, it never made it into the standard today. I know that Arthur O'Dwyer is working on an implementation and also on a proposal to actually make unique pointer check that you never allocate a derived class and then migrate it to a unique pointer over the base class if the base class doesn't have a corresponding virtual destructor. And then there are classes where you actually define a destructor with the body. Destructor bodies must not be empty according to the MISRA rules, and that means that you are managing a resource. My personal guideline is never attempt to manage 2 resources at once. That's very tricky to sum up. So if you have a class that needs to manage 2 resources, make a manager class for each of the resources and combine them as regular members. And then you can apply the rule of 0 again, because the compiler provided constructors and destructor will just do the right thing. And there are several flavors of managers. The easiest to get there is a scope manager. And if you want to learn how to implement that, come to my workshop on Sunday. It's a repeat of the workshop yesterday. There are manage and the scope manager compared to a scope log that allocates or a resource on construction and implicitly releases it on destruction. We have the ability with move operations to transfer ownership of resources. That's where unique manager is coming, and unique pointer is the classical canonical example of a unique manager. And then there are resource managers that are copyable, usually because the resource itself is copyable, and that might employ the optimization of a move operation for, let's say, actually transferring ownership of a resource instead of copying it, because that might be expensive. And standard vector is such a general manager object that has this implementation. And this is something I wanted to teach you today, and that you can actually take home with you without relying on the MISRA guidelines. And if you implement copy and move, you might not know, but there are interesting means of actually spelling out copy constructors and move constructors, or copy assignment and move assignments. I don't want to show that to you, but these are the means to actually spell out a copy constructor. You pass the right-hand side by const reference, and a move constructor takes by R value reference. If you provide an assignment yourself, then there's one innovation that MISRA-C++ gives you. It requires you, if you define it yourself, you may have to make it L value ref qualified to avoid applying the copy assignment operator to a temporary, which will return an L value reference to a potentially dangling thing, because the temporary might be cleaned up afterwards. That is an innovation that MISRA-C++ will provide to you. There's an exception. You can return a void here, which prevents using the result. So then you don't have to specify the ref qualification. But again, it would make much sense to have temporary and change it on the fly. Now, stepping away from MISRA-C++, the other working group that takes care about quality C++ code is the ISO JTC1 SC22 WG23, and it's about programming language vulnerabilities. At the beginning, I talked about that, and what's in there. There's a general document that is a technical report. Therefore, I think it's freely available by ISO instead of the overall standard, but they will change that to become an ISO standard. I'm not sure if it will stay free or you have to pay for it. And that's collecting general things that can go wrong. There are special volumes for Ada, for C, and other languages that address how these general vulnerabilities are actually happening in those languages and can be mitigated in those languages. And the -3 one is for actually the C language, and the -10 one is for C++. And some languages might have extra vulnerabilities that are not part of the general vulnerabilities, but those extra things sometimes will also feed back into the general ones once they have been discovered, and because they might apply in other languages as well. Example rule. So this is one example of the general things. Okay, if your language provides pointer arithmetic, there are mechanisms of failures, like, okay, you produce a memory location that is arbitrary, that's outside the bounds of a buffer, for example, that might, if it's used for code execution, provide you with arbitrary code execution. Usually modern hardware tries to prevent that today. and you might actually address memory outside the range of a program, and you have an operating system that doesn't have memory protection, that would allow you to read memory from another process, like let's say Windows 3.1 allowed you, because its underlying base was the DOS operating system that wouldn't actually have memory protection at the time. And applicable language characteristics, okay, the language does allow pointer arithmetic, so actually modifying pointers, not all languages allow that. For example, Pascal wouldn't allow that facility because there was no such thing as a pointer arithmetic. And how can you avoid that? Okay, don't do pointer arithmetic and prefer indexing for arrays, but that only works if it's implemented differently from C and C++, where indexing to a plain array is actually doing pointer arithmetic. So it's a synonym for pointer arithmetic in C and C++. So that's not a mitigation that works in those languages. For C++, the example, if you look at pointer arithmetic, it's applicable because we have that, we are allowed to do pointer arithmetic. And also, if you use iterators that are random access iterators, even if they are not implemented as pointers, you suffer from that by the ability to advance or use standard next or standard pref to actually move the pointer around and get to a point where you're no longer addressing the actual underlying container. And there are other guidelines, there are plenty of guidelines that relate to pointer arithmetic. There are others that care about buffer boundary violation, which is most of the time what happens when you have a pointer arithmetic problem. And one thing that comes from the C++ core guidelines, prefer standard algorithms over handwritten loops, because there you usually pass a range that is guaranteed to work, or a begin and end iterator, and hopefully you pass the correct values to not have out of bounds excesses. MISRA actually considered an outright ban on pointer arithmetic, but I'm not sure that's a mandatory or required rule. But my recommendation is don't use plain pointers in code. And we learned that also yesterday in my workshop, and how to get rid of those situations where you would use plain pointers today. And the good thing is I moved the working document and to GitHub to work on these vulnerability guidelines for C++, and you can have a glimpse of the underlying project stand on because we generate a website from it. In a public space, the actual work happens in a protected space. But if you want to contribute, you might be able to join the effort. You should contact me, and I will forward you to the project editor of and the chair of the working group, and we will see if you could contribute. And contributions are needed because we meet about once a month or maybe every 3 weeks virtually, and it's still a lot of work to do, and also done by volunteers. So the progress is as fast as the volunteers have time to actually work on it. And that means it's not that fast to get it done, to get it completed. If you want to just give feedback, you can use that GitHub repository to provide feedback. We already got feedback, and usually it means that we ask you to phrase something and then incorporate that into the officially working document. So summing up, many safety guidelines are retrospective. So adhering to a guideline doesn't mean your code is perfect. It just means, okay, you did well, but you might actually have still issues with the code. So static analysis tools that figure out adherence to guidelines are not the only means to make your code safe. If it's really about safety critical or security-related stuff, have other means to get your code done right. For example, automated testing on all levels, to fuzzing with the tests to actually check if your code behaves well, if it's getting unexpected input, and also have humans to review your code and improve on their findings. And don't be shy to show your code around, because that allows you to get feedback. What you also should know, you cannot check for hardware errors. So if you're designing an overall system, there might need to be extra hardware checks to check for failures of hardware. If you launch a satellite, for example, or even an airplane that flies very high, you should make sure that you have hardware memory protection, or maybe even hardware protection for the bits in your processor. And there is special hardware that costs about 100 times maybe of the regular ones, but it might be worth the value. Or you might have to need other means of redundancy in hardware to check for hardware errors. Also, if you have software that creates the safety, always have a save mode. So if you cannot guarantee working of some external system, have a means to actually live with that and continue operation. That's also worthwhile in a let's say in a security environment or a 24/7 environment, where you better have at least show a web page that something is happening, instead of getting an error from the browser, oh, the connection timed out, for example. And take home with you as cons as possible. And I would say East cons is the way to go, but that is something whenever we meet again, we can fight over a beer. And limit and encapsulate the use of volatile if you're in a hardware near system, and be aware of the resources that allow you to check for vulnerabilities. Use static analysis tools. Some are available for free, some are need licenses, but don't be shy to convince your superiors to buy them for you or spend the money yourself. And please help with the work. There will be a round of MISRA-C++ guideline feedback, or several rounds of that. So if you're in that domain, please give us feedback to help to improve our work, as you should ask for feedback for your own code. I think I'm done. We have a couple of minutes left, and there's a whole lot of questions. I won't be able to read the chat right now, but let's look at the questions. I need to read them. So the question is, how can we separate between personal preference rules and scientifically proven rules? And that is something, yeah, there's opinionated things. And the good thing is you can deviate from the rule if you have a reason. And considering the rule being opinionated, that is something that would pass my review. If you say, okay, that rule is opinionated, we have another opinion. And if you state that explicitly, then that's a good means to deviate from such a guideline. And sometimes the opinion comes from actual thought, but if your thought processes differ, I think that's okay to deviate. Now, I see the next rule. What sort of overlap is there between MISRA and Clang Tidy static analysis? Are there some MISRA rules that could be added to Clang Tidy? Sorry. I would say I'm not familiar with the overall rule set, what Clang Tidy does, because I'm not using it actively at the moment, because Develop has its own set of guideline checks. Many of them were inspired by me, or actually forced onto my students by me. Therefore, I'm not an active user of Clang Tidy. But I'm sure there is overlap between MISRA and Clang Tidy, and there might be rules, MISRA rules that I believe Clang Tidy is built on Clang, so it does a single translation unit thing, and there are definitely MISRA-C++ rules that are across translation units, whole system rules, and I'm not sure if you are able to implement those easily in Clang Tidy, but I'm too unfamiliar with the current architecture of Clang Tidy if that's impossible or not. And therefore, if the rules are published, I think you are very welcome if you implement those that are missing and that are possible with Clang Tidy to do them in Clang Tidy. So which static analysis tools I use myself? I use the compiler warnings. I usually enable all warnings or most of the warnings. Sometimes I have to deviate, but then I individually turn off the warnings. I use Clang and GCC. Since I don't, I'm living on a Macintosh computer or Linux computers, I rarely employ the Microsoft compilers or other compilers that you have to pay for. But if I have something that is interesting, I might actually employ the Compiler Explorer by Matt Godbold to figure out if it compiles on other compilers as well. And I use the static analysis tools that my students and my team built for Develop, and they actually provide also many of them provide the ability to have immediate remedy by quick fixing the corresponding code position, like adding a const that is possible on a key click, not even needing to write const there. The semantics, there's another question on the use of volatile. Volatile does say something, but the semantics of volatile as specified in the C++ standard might be different from what you think it means. It is there to guarantee memory reads and writes happening, but doesn't mean that another thread sees those reads and write in a timely manner. So volatile atomics, as stated there, they just work as you might expect them. So if you have a volatile atomic, that's how you do volatile today for inter-thread communication. But if you have arbitrary volatile variables that you share across parts of your system, you might not get the effects of what you intend to. There is one bigger area. If you use a shared memory for inter-process communication, then the shared memory is better behind a volatile pointer because another process might have changed the underlying memory, and you want to be able to read that changes, and not having the read optimized away by the compiler. Oops. I'm not sure I clicked away another thing. So there's the question about sharing the links and reference. I think I will either put them on Discord or Twitter so you can actually see where that is. I will do that after the session is over. Then is GoTo considered harmful? Yes, it is, because MISRA-C++ 22x will allow return statement, and it will disallow GoTo, but with all the required rules. You can have a GoTo if you write a deviation and have a good reason to do so, and there is code where you might want that. But in C++, the need for GoTo error cleanup is no longer there, because you have the ability to implement your scope managers that will clean up in any case, even in an early return or throw in an exception. And that is why the need for GoTo is really neglectable, and I would review your deviation if you want to use GoTo, and maybe just refactor your code to show you how you don't need GoTo there. And there's another question. Okay, atomic also works without atomic, which means atomic also works without volatile, and that's true. And I'm not an expert in that domain, but there are experts that might actually recommend to write a volatile atomic. I don't know the exact situation, if and where that might be necessary, but at least it's not wrong. And I think I'm done with the questions, and time is running up. And thank you for having me, and thank you for those who stayed throughout. I didn't look at the attendees who actually left in between, but I hope you enjoyed the talk, and I will be around the conference, maybe not all the time, because from home, it's not like you're locked into the hotel. There are other obligations to fulfill. And I had my second COVID vaccine shot today. So tomorrow might be a day where I have to be very passive because fever might kick in. So don't expect me to be too active tomorrow. But nevertheless, I'll be with you. And if you can reach me through Discord or Twitter or email, and you should get my contacts, and my name is I'm easily to find with Google again. So goodbye altogether, and take care of yourself and enjoy the rest of the conference, and see you around.